See if we can get that to work. Just a little better. Cool, thanks everyone for sticking it out. I guess that took a couple minutes, but no big deal. I'd like to start by thanking everyone involved, especially the American Homebrewers Association for putting on the 2011 National Homebrewers Conference and having me here to speak to all of you today. My talk today is about brewing with Brettanomyces. It seems to be a big thing, and this is how you can use this yeast as homebrewers. So first I want to talk a little bit about, as I said, Crooked Stave and kind of what we're doing with Brettanomyces beers and where we're going with those. So I studied a degree in brewing and distilling, and what I really concentrated on was Brettanomyces yeast. My dissertation was titled Pure Culture Fermentation Characteristics of Brettanomyces yeast species and their use in the brewing industry. After that, I went to work and worked as a brewer for Odell Brewing Company, working on such projects as Saboteur, Freak, and Deconstruction. These were different barrel-aged Brettanomyces beers. From there, I left to start Crooked Stave, and actually just opened Crooked Stave in November 1st, 2010. And it says June here, but that's wrong. January 10th, 2011, we brewed our first batch. And our first batch was a 100% Brettanomyces primary fermentation in oak barrels, which is still aging away. And sadly, it was the beer actually that I brewed, hoping to be able to bring for this and to have here. As you guys can tell, you don't have any beers in your hands. So I really apologize about that. But yeah, we've been filling barrels. Our first thing was to get as many barrels as possible filled. And we've got some 100% Brett fermentations right now in the fermenter. And the foeder just aren't quite ready to bottle and bring for you guys. So I apologize for that. But what we're doing is we've got a series of beers called Wild Wild Brett. It's a 100% Brett primary fermentation and kind of playing around with different ways that different yeasts can be used. There's many different kinds of Brettanomyces, just like there's many different kinds of Saccharomyces strains. You know, you might use one for a wheat beer and another for an English ale. It's kind of the same thing with Brettanomyces, just there's much less, but they're to be discovered. So the idea is kind of to showcase these yeasts and show their diversity. We're also doing lots of barrel-aged sours, and that's kind of what we've been doing right now, is filling barrels. Some of these are actually primary fermented first with Brettanomyces, and then just souring afterwards. Beers like the Brett d'Or, Nightmare on Brett Street, Mauricio. And then playing around with, as we'll talk about this a little bit more, playing around with different mixed cultures and hybrids. So we've got a petite sour that's partial Brett primary and spontaneously soured wort, blended in a large foeder, and just kind of beers like that. So that's kind of our goal as a project right now, is being able to brew these different beers with Brett and showcase kind of their use. I'm going to go over kind of quickly a little bit of background of Brettanomyces, kind of explain that and stuff. Hopefully it's either catches people up on stuff they already know, or we'll kind of showcase a little bit, and we'll help kind of explain, you know, what's known about this yeast in ways that it can then be used at home and home brewing. So you've got Brettanomyces or Decra. These are more or less the same organism. The name can be used interchangeably. Brettanomyces, as we generally refer to it, is the asexual reproducing form, known as an anamorph. So this is the form that buds off to reproduce, just like we see kind of with our Saccharomyces strains. And then there's Decra. Decra is the sexual reproducing form. And in brewing right now, we're only concerned with the budding form. We don't really see the Decra and everything. So it's kind of appropriate to call it Brettanomyces, even though genetically they call it Decra. The original nomenclature, so this is back from the early 1900s, 1940s, when people were starting to culture Brettanomyces. They were just coming up with a bunch of different names: Bruxellensis, Lambicus, Intermedius, Castercii, Pausinii, Animalis. The list really goes on. Today, the current nomenclature, there's 5 strains of Brettanomyces. So you have Brettanomyces bruxellensis, Animalis, Castercianus, Nardensis, and Nanus. And then for the perfect state, the telomorphs, Decra bruxellensis and Decra animala. And the reason why I kind of make mention of this is it's kind of been made confusing with which strains are actually strains and which are species and everything. And so the yeast companies will name strains based on some of the old nomenclature, based on characteristics of those strains. So that's why you can get Brettanomyces lambicus or Brettanomyces pausinii. As far as like the species goes, it's actually Bruxellensis and Animalis. So the lambicus has been reclassified as Bruxellensis, and the pausinii as Animalis. But for naming purposes and for the differences among these companies, will continue to call it a lambicus or a pausinii. And it's kind of thought of basically as a name and something to differentiate them. One of the things that I get asked a lot is, well, how can a Lambicus now be a Bruxellensis when I've used both those yeasts and they're both quite different? And the best way for me to explain that is, it's the same way as like the difference between a Belgian Saccharomyces strain and an English Saccharomyces strain. Both of them are Saccharomyces cerevisiae. It's just a little bit of difference in its genetics. And that's kind of the same thing between the Bruxellensis and the Lambicus, or the Clausenii nanomolis. I'm going to go through some of this a little bit quickly, but this is kind of the early initial discovery and characterization. The earliest published account of Brettanomyces was from 1904. Actually, the Institute of Brewing, which is out of England, even though it was by a Danish professor or a Danish researcher, Clausen. And he proposed basically in this long write-up that the yeast be called Brettanomyces because it was a British brewing fungus. And he basically said it was responsible for the secondary fermentation and development of the characteristic flavors and aromas associated with the finest English stock ales. At that time, English stock beers that were being held over for longer amounts of time were put into barrels, sometimes unlined casks, sometimes lined casks. Either way, they always had the secondary fermentation, or almost always, with Brettanomyces. And this was when the brewing industry was starting to move towards pure culture fermentations. But whenever English brewers would use these pure culture fermentations, they never got this same quality out of theirs. And this was where the research went in first discovering Brettanomyces yeasts. It wasn't until 1940 when the first systematic investigation was presented by Custers and his findings on 17 strains of Brettanomyces. At the time, Custers believed Brettanomyces yeasts were only found in English and Belgian beers, and as we now know, it's not. It's a yeast that's found all around the world in every winemaking region. And I simply just make that statement because a lot of times Brettanomyces gets categorized as a Belgian yeast. And certainly we see it coming out of Belgian beers some the most, and it's what we associate it with. But it's not. It's found in every wine region, and wines throughout the world, and in this room right now, not on me. Custer's thesis. This is where we get a lot of the information, and actually misinformation about Brettanomyces. Everyone's kind of ran with the fact that fermentation of glucose to ethanol occurs more rapidly under aerobic conditions than anaerobic conditions. And Custer's termed this negative Pasteur effect. What he was talking about when he was talking about that was looking at it like, as he puts Brett into a small little jar and starts measuring what's coming out, he found that under aerobic conditions it was faster than anaerobic. He wasn't talking about a brewer's fermentation, what we're considering. I mean, it's standard when we use Saccharomyces that we don't see fermentation take off for 24 hours. But that's not what he was talking about. He by no means was talking about a complete fermentation or a brewer's fermentation, just simply the metabolism at a given point right off the bat. He also found that considerable amounts of acetic acid were produced during aerobic conditions, while no appreciable amounts were formed during anaerobic conditions. The anaerobic conditions is something that's always left out. People associate rapid spoilage with acetic acid, but under a standard brewer's fermentation with anaerobic fermentation, generally have very little, if sometimes less, acetic acid produced in the Saccharomyces strains. And Custers believed that cells slowly became adapted to anaerobic conditions, eventually resulting in a normal anaerobic fermentation. And lots of researchers have actually gone on to show that, yet the brewing industry has never really looked at it. So Custer's effect. Custer's effect was later introduced in place of the negative Pasteur effect, and it was used basically as a way to introduce and interpret the glycolytic activity. Basically, as the yeast cells, the Brettanomyces yeast cells, were switched from an aerobic to an anaerobic phase, the glycolysis, which is the breakdown of your sugars to pyruvate, comes to a temporary stop. The transient lag phase was observed to last about 10 hours before a slow dissimulation of glucose and more CO2 resumed. Here we just kind of got a little bit about that. And it's basically biochemically kind of what was going on. It's just from NAD+, irreversibly not being converted to NADH. And what they found this to be caused by was a metabolite, glycerol, that wasn't being produced. This is kind of important because yeast produce glycerol, and it's got a secondary role in enhancing the perception of body and mouthfeel. A lot of people talk about in Brettanomyces fermentations that it's a dry beer, it lacks mouthfeel. And this is probably one of the reasons why. It's because it's not producing glycerol. After all this, researchers again found like a slow adaptation of Brettanomyces yeast metabolism during anaerobic conditions, followed by the lag phase, showing that it is possible to do pure culture fermentations with Brettanomyces. So the fermentation capabilities of this yeast. Brettanomyces is really unique compared to some of the Saccharomyces brewer strains we use. It has two really unique and important enzymes. The first one is alpha-glucosidase. So this is the enzyme that's responsible for over-attenuation that's seen in lambic or any of your sour beers. And basically it's an enzyme that's capable of breaking down larger wort dextrins. So where usually we talk about maltose, maltotriose being some of the largest ones that Saccharomyces can break down, Brettanomyces can continue to break down malto-oligosaccharides. So these are just larger dextrins with up to 9 glucose molecules attached to it. The enzyme functions by cleaving off a glucose molecule and forming the next smaller. So it continues to make glucose, make glucose, make glucose as it slowly shrinks these dextrins down. And there's both an extracellular and intracellular form, which is really interesting that it's able to do that both outside the cell and inside the cell as it's taking in the sugars. The other one is a beta-glucosidase. And some people have heard about beta-glucosidase from the Clausenii or the Anamala strains. And the beta-glucosidase enzyme, that's the one that's able to ferment lactose. So where you would normally make, say, like a milk stout, and you know that the lactose that you put into it is not going to ferment out, the Brettanomyces is able to ferment that, as like some bacteria are that make, say, yogurt. The other is cellobiose. Cellobiose is a sugar that's from the breakdown of cellulose. Cellulose is a lignin that's found in plant material and in wood, like oak. And the other are glycosides. Glycosides are compounds that are found in various hops, fruit, and spices. And that's actually a really interesting aspect that I'll be able to talk about later, because that's new flavors that Brettanomyces can be used to produce that didn't originally exist. So some earlier studies basically looked at the Clausenii. The Clausenii and the Anamala strains are the ones that appear to be able to ferment lactose and cellobiose, as well as being able to actually produce ethanol from them, so an actual fermentation. And one of the other things that's really interesting is that Brettanomyces yeast are most commonly cultured in beer conditioned in oak barrels. So symbiotic relationships kind of always been inferred through that, and given the longevity of their existence, seems like a good place where Brettanomyces would continue to live. That would be from maybe the fermentation of cellobiose or cellulose. But most of the Brettanomyces strains that are found during lambic and sour beer brewing do not have the necessary enzyme. So it's simply that the Brettanomyces cells are actually so small that pores within the wood are a great place for them to be able to hang out, to hide, and as long as they stay moist and have a little bit of nutrients, they're able to just keep going and living. So production of secondary metabolites. This is far and away the most significant aspect of Brettanomyces yeast. It's their ability to influence the flavor and aroma of beer. When we look at our fermentations with Saccharomyces, we know that our esters are formed like in the first 36 hours. And after that, we don't continue to see big flavor development. And that's why sometimes we'll ramp up our beers to try and do further attenuation. But we're not so worried with that flavor contribution because it's just not going to really continue to give us that. Brettanomyces is completely different. So when we're using it in secondary fermentation or anything like that, we can pitch it. There's minimal nutrients, minimal sugars, and Brettanomyces actually has the ability to take those compounds and continue to make new esters, new flavor profile compounds, and continue to go. And that's really important in Brettanomyces and using it for aging and going on. So it's one of the aspects that researchers have been the most concerned with, especially in the wine industry, because as soon as you get the Brettanomyces infection, they see it as a really bad thing. So there's a lot of organoleptic disruptors. There's a lot of flavors that are associated with Brettanomyces. And I've got up here, I think, clove, spicy, horsey, barnyard, smoky, medicinal, band-aid, metallic, cracker biscuit, goat-like, cat piss, apple, floral, tropical fruit, and citrus. So some of those positive, some of those negative. I guess it's up to you to decide what you want in your beer.